Good day everyone, welcome back to our channel. Today, we're delving into a specific aspect of thermal properties that plays a crucial role in countless processes: the surface transfer heat coefficient. Get ready to explore the fascinating world of heat exchange at the surface level. Heat transfer coefficient is a quantitative characteristic of convective heat transfer between a fluid medium, a fluid, and the surface wall flowed over by the fluid. Convective heat transfer is the mode of energy transfer between a solid surface and the adjacent fluid that is in motion. And it involves the combined effects of conduction and fluid motion. The surface heat transfer coefficient, often represented by H, measures how well heat is transferred between a solid surface and the fluid around it. This coefficient is crucial for figuring out how fast heat is transferred in many engineering applications, such as heat exchangers, cooling electronic devices, and climate control systems. Example: when a water-filled container is heated, conduction heat transmission happens within the water at the container's bottom. In addition, the heated water rises due to buoyancy, and convection occurs along the container's edges, resulting in additional heat transfer. Conduction at the bottom of the container, where the heat source is applied, conduction heat transmission occurs. Conduction is the process by which heat is transferred through direct molecular interactions within the material. In this case, the heat is transferred from the heated bottom surface to the cooler water molecules in contact with it. The energy is passed from molecule to molecule, gradually increasing the temperature of the water at the bottom of the container. Buoyancy and natural convection. As the water at the bottom heats up, it undergoes thermal expansion, causing a decrease in density. This decrease in density creates a buoyant force, causing the heated water to rise. This phenomenon is driven by buoyancy, where warmer, less dense fluid moves upward, while cooler, denser fluid moves downward to replace it. Convection along the edges. The upward movement of the heated water due to buoyancy sets up a convective flow within the container. This flow enhances the heat transfer process. Rising warm water, the warmer water rises along the edges of the container. As it ascends, it transfers heat to the cooler surrounding water and the container's surfaces. Descending cool water simultaneously. Cooler water from the top of the container moves down to replace the rising warm water. This cooler water is then heated by conduction at the bottom. Continuing the cycle, the convective currents created by this movement result in a continuous circulation of water within the container, significantly increasing the overall heat transfer efficiency. Formula: QH at Q is the heat transfer rate W. At is the surface area N. T sub S is the surface temperature C or K. T sub infinite is the fluid temperature away from the surface C or K. Units. The surface heat transfer coefficient TONC is measured in watts per square meter per degree Celsius WMC or watts per square meter per Kelvin WMK. Factors: fluid properties, thermal conductivity, viscosity, density, and specific heat capacity of the fluid. Flow characteristics: flow velocity, flow regime laminar or turbulent, and turbulence intensity. Surface geometry: shape, size, and orientation of the surface. Temperature difference: the greater the temperature difference between the surface and the fluid, the higher the heat transfer coefficient. Surface roughness: rougher surfaces generally enhance heat transfer by disturbing the boundary layer. Next is the practical considerations. Experimental determination and enhancement techniques. Experimental determination is the heat transfer coefficient is determined experimentally for specific conditions and geometries. Experimental determination refers to the process of measuring and quantifying a physical property or parameter through direct observation and experimentation, rather than relying solely on theoretical calculations or assumptions. This approach is fundamental in scientific research and engineering to validate theories, understand phenomena, and gather empirical data. Key aspects of experimental determination. Preparation defines the objective of the experiment and identify the property or parameter to be measured. Gather the necessary equipment and materials, ensuring they are appropriate for the experiment. Set up arrange the experimental apparatus according to the requirements of the experiment. This includes positioning sensors, ensuring proper insulation, calibrating instruments, and setting up any control systems. Execution conduct the experiment by applying the required conditions such as heat, pressure, or chemical reagents. Monitor the process closely, making adjustments as needed to maintain stable and controlled conditions. Data collection record measurements using appropriate instruments. Ensure that data is collected consistently and accurately, often at multiple points to account for variability and enhance reliability. Next is enhancement techniques. Techniques like fins, ribbed surfaces, or turbulators can increase the heat transfer coefficient. Enhancing the surface heat transfer coefficient is critical for improving the efficiency of heat transfer processes in various applications. From industrial systems to household heating and cooling devices, several techniques can be employed to enhance this coefficient, leveraging both passive and active methods. Understanding and accurately determining the surface heat transfer coefficient is crucial for designing efficient thermal systems and optimizing heat transfer performance.